Hello everyone, my name is Gong Mingyang from National University of Defense Technology. This presentation is about our work, fine-grained code comment, semantic interaction analysis. Other authors are Wang Shangwen, Dong Dezun, Gu Shanzhi, Hongfang, Ruan Weijian, and Liao Xiangke. Let me first introduce the motivation of our work. Here is an example from the Spring Security open source project, and the comment is written by its developers. Although the comment describes the functionality of the source code specifically, developers still do not know which part of code corresponds to the specific contents. For example, tokens in the comment with only the plain comment on hand. Therefore, existing methods do not explore the fine-grained matching relationship between code and comments, which can boost the program comprehension. Given this, we believe that showing the fine-grained code comment semantic interaction is beneficial for program comprehension. From this example, we know that all the contents in the comment can semantically match with a part of the source code. For instance, the verb return in the comment is related with the return statements in the code. Therefore, fine-grained code comment semantic interaction analysis is beneficial for program comprehension. Now, we introduce our method to solve the above problem. Here is workflow of our method Foster, a downstream model with transformer-based image and text encoders. On top of the image and text encoders, the representations of textual tokens and visual tokens are linearly projected to the multimodal joint space. A novel fine-grained contrastive learning equipped with cross-modal interaction is proposed. This exploits a token-wise maximum similarity between visual and textual tokens. The image encoder is a Wilson transformer. Each visual token is split by line to preserve the original semantics. Similarly, the text sequence is first tokenized and then divided into text transformers. Finally, a cross-modal interaction mechanism is exploited to compute the similarity between each token and image patching and model token-wise cross-modal interaction. For the contrastive loss, the cross-modal interaction is reflected in how we compute the similarities for the S image and the J text. For the case visual token, we compute its similarities with all textual tokens of X and use the largest one as the token-wise maximum similarity with X. We then use the average token-wise maximum similarity of all non-padded tokens in the image as the similarity of the image to a text. As for the dataset for evaluation, as far as we know, there is no available dataset for this task. Therefore, we first collect code and the corresponding comments from 10 randomly selected GitHub repositories from the test set of Java part in CodeSearchNet. Then, the visual renderings of source code are split into statements by line, and comments are split into tokens by blocks. Finally, a two-dimensional matrix should be labeled, which indicates whether the token in the comment has semantic relations with the corresponding visual patches. To assess the effectiveness of our Foster, we propose to answer the following research questions. RQ1 aims for effectiveness. RQ2 aims for efficiency. RQ3 aims for practicability. To evaluate the effectiveness of Foster, we use the widely adopted precision, recall, and F1 score metrics. For a baseline method, it first generates a series of code mutants, where a mutant is a slight modification of the original code. By taking each code mutant as an input for the neural machine translation model, it can generate the corresponding comments. Then the baseline can determine whether the mutant affects the generation of each focus and discover the fine-grained interaction relationship. From the results, we know that Foster achieves relatively high precision and recall. Specifically, the overall value of precision reaches 82%, which means the semantic interaction pairs reported by Foster are of high probability to be correct, and recall reaches 77%, indicating that most of the real semantic interaction pairs are identified by Foster. The results of the time consumption of Foster under diverse configurations are shown in Table 6. We can see that all the three strategies can optimize the efficiency of Foster to a large degree. To answer RQ3, we invited 4 PhD students in our college majoring in software engineering to help us assess the usability of the prediction results of Foster on program comprehension. For each code command pair, we show them the semantic interaction results from Foster and ask them if they think the result is useful for them to better understand the code's name compared with the pure command. The comprehension is reflected by the understanding of the intention of each variable and statement. The results demonstrate the rationale of the basic point of our study that building accurate code command semantic interactions can boost program comprehension. We mainly find that Foster is good at capturing the semantics inherent in the control statements, like if control statements. As shown in the above example, Foster made good predictions for tokens corresponding to the control statements. Nevertheless, Foster does have some limitations. The most significant one is that, as pointed in our user study, it tends to miss semantic information from method signatures. Specifically, a number of command tokens should have semantic relations with the method parameters, but Foster does not make such predictions. In conclusion, Foster can effectively capture the fine-grained semantic interaction between visual renders of source code and comments compared with the heuristics-based baseline approach. Second, Foster can be applied in practice with affordable time consumption. And three, programmers consider the prediction results of Foster as useful for better understanding the code for most conditions.